Now that's an entrance. Right, thank you very much for making it back from coffee. I know what these Monday morning sessions are like, so I really appreciate you making it back on time. As Sydney said, I'm Ollie Perks. I'm a field application engineer at ARM, and I will stress at the start of this, I am HPC. I am not AI machine learning, so I've got a few slides on that that hopefully I will talk to later, but my background is on more traditional HPC side of things. So ARM, this is one of our fantastic stock slides that I find really does get the message across that 70% of the world's population are using ARM technology. And actually when you look at it, it's not just one piece of ARM technology, it's multiple devices, multiple technology lines that are going into everyday use by a significant percentage of the world's population. And that's great, but let's face it, that's mobile phones, and that's not really what we're here today to talk about. So I really want to show kind of how ARM has come into high-performance computing and where ARM is going into future generations of high-performance computing and into AI and machine learning. So this is my kind of personal slide on the background of ARM in HPC. Obviously, this predates my time at ARM working on it, but I date it back to around 2011, the rise of the kind of Calxeda boards, which were fantastically innovative, but sadly didn't go anywhere. But since then, there's been a long legacy of chip development and manufacturers making ARM-based technology to really look at breaking into the server market. Some had more success than others, but where we sit today is around about these two lines. So we've got the Marvell Thunder X2, which I'll be mentioning quite a lot about today, and we're all looking forward to this Fujitsu A64FX for a number of reasons, and I'll touch upon that in a second. But what it's worth pointing out is there's been an awful lot of progress in this 10-year time span. And whilst we came from a very mobile phone-centric perspective, and can we use lightweight phone cores in HPC, we really are now at a stage where we're targeting big, beefy CPUs for server, HPC, and scientific computing. And that's where we're heading. So the Marvell Thunder X2 has had many names over its lifespan, so forgive me if I refer to it as the Cavium Thunder X2 at any point in this, but we're talking about the same chip. So it's a 32-core socket. Generally, the high-end SKUs, we're talking about 2.2 gigahertz, 4-way SMT if you want to use it, and it's a full out-of-order core. So this is a serious CPU. And really the defining factor about it for use in HPC and scientific computing and everything is this additional memory bandwidth. So it was decided to really look at the needs of large-scale workloads in HPC, server, scientific computing, kind of wrapping those all into one, and the dependency on memory bandwidth, and saying, well, can we address that? Can we design a chip with not just lots of cores, but lots of memory bandwidth in it as well? And if we do, does that actually answer the needs of application developers? So this is what they did. They put 8 channels of DDR4 in to each socket. So obviously we're talking dual socket systems. So we're getting about 250 gigabytes a second of stream bandwidth, which is really impressive. And for certain applications, we're actually seeing real benefits of using that. So I've got some application numbers later, and just bear that in mind that that's one of the kind of key differentiating factors. Other than that, it's a normal socket, normal chip. But I really want to highlight this line, and apologies I can't point at that slide as well. This is 180 to 200 watts a socket. This isn't a mobile phone processor. This isn't how do we take something that you'll find in an iPad and stick it into a chassis and try and get your applications on it. ARM doesn't mean low power. ARM means configurable to silicon partners who want to manufacture chips. And if they want to manufacture low power chips, they can manufacture low power chips. If they don't and want server class chips, then they can manufacture server class chips, all based on the same IP and the same instruction set. And that's exactly what Fujitsu have done for this A64FX. And this came out of predominantly a collaboration with the Riken Institute of Science in Japan. And it was, how can they take their existing CPU designs, which were based on a Spark architecture, and really design that in a technology that has more of a community built around it. Obviously, Spark, for all of its pros, doesn't have the same kind of community and active development happening around it as something like ARM does at the moment. So this was a real commitment by Fujitsu and by Riken to look into the possibility and the reality of designing their new core based on ARM technology. And when I say design, I really mean design. So ARM licensed the instruction set to them, but other than that, this was a real kind of end-to-end design by Fujitsu. And so there are a lot of characteristics about it that will mimic the Spark design to make it easier for their application developers to take their code and move it to this new architecture. But the really important things that I want to highlight about this chip is it will be the first publicly available CPU with SVE vectorization. This is ARM's scalable vector extensions with a vector length agnostic architecture, but Fujitsu will be using a 512-bit vector length implementation. So they have very strong vectorization performance, and on top of that, they've done away with DDR memory and just implemented high bandwidth memory Gen 2, and they're looking at 4 stacks with a combined 1 terabyte a second of bandwidth. So they've designed this core and a socket based around it with 48 cores, lots of vectorization and lots of memory bandwidth, and a direct connection to their Tofu 3 interconnect. So this was a real custom design for their needs, and it's really built from scratch of the needs of the applications. So they really targeted the 9 key application areas that they use for the production science at the Riken Institute, and said, what do we need of the next generation of CPU? And this is about a 10-year project to get this to market for them. So this is coming online later this year. We've got first versions of it appearing now, and for those of you at supercomputing, expect to see the first stage of performance results being published on this. But this is causing a lot of excitement within ARM and within a lot of our partners. But we're not there yet. So what have we got? Well, the Thunder X2 is, let's say, the showcase of ARM server technology at the moment. And so we have a number of systems that are built and deployed running it. The largest and arguably most famous of the systems is the Astra system, which is deployed into Sandia. And this is, I had to revise my slide, as unlike most systems on the top 500, this actually went up on the last list as they were able to bring more of the nodes online. It's now at position 156, which, whilst isn't massive, was a real showcase that ARM technology, through all of the integrators, so this is an HPE system, could actually be brought together and make a viable production platform. Now, obviously Sandia is a very large national lab. They have a lot of money to invest into research and development, especially with new systems. So this was a test bed for them, which is laughable at the size it is. compared with a lot of the systems we have in the UK. But they really wanted to evaluate whether this was usable for their production science. So in the course of the last, I believe, 2 weeks, this system has moved from the open side onto the restricted side, so that Sandia can actually start looking at their production classified workloads and evaluating their use on the ARM technology and on the ThunderX2 chip. Now, obviously, their end goal isn't a ThunderX2 production system, but they're looking forward onto how they can work with ARM, work with our partners to co-design future generations of ARM technology to deploy systems that really benefit their production workloads. Inside the UK and Europe, we've got the Isambard system, which gets a lot of publicity. It's a fantastic system and is, again, quite interesting as it is a Cray-based system. So this is everything that you would expect from a Cray system, with the Aries interconnect, the Cray software stack, everything that you would expect, but with a ThunderX2 socket driving it all. And they've got just over 10,000 cores of this, and this is running, actually located at the Met Office, but driven by Bristol University. And I would add for this and my following slides, these systems in the UK are doing production work, but also they're available to access by industry and academia as testbeds for people wanting to evaluate ARM hardware. And that's something that's key to us at ARM. So the Catalyst project is something quite close to our hearts here, as we've deployed 3 systems, again in collaboration with HPE, one into Edinburgh at EPCC, one into Bristol, and another one into the University of Leicester. So we do a lot of collaboration work with Mark for our Leicester system, and each of these systems is nominally identical from a hardware perspective. So they're 64 nodes making 4,000 cores, again using this ThunderX2 technology, but where they differ is all 3 of the sites are targeting different application workloads, different software stacks, different variations in how they run and deploy their systems in accordance with their local site policies. And again, these systems are really being used to evaluate the viability of ARM for the diverse application workloads that all of these centers have, but also the collaborators that all of these centers represent. So this is another system, or another collection of systems, where we're really encouraging people to get access to them, to try their codes out, to see what can be made of both the architecture and the software ecosystem, and then feed that back to us, to the partners involved in the project, and really reinforce everything to make the best experience for future people accessing ARM systems. So I just wanted to put this in as an honourable mention. It's not all Cray and HPE. Atos are also deploying ARM-based systems, and actually this is currently the largest ARM-based system deployed in Europe, at 292 blades, and again running the same ThunderX2 socket and same 32 core design that the other systems are built on. Unfortunately, they've not made too much about this system in the press, so there aren't too many details, but this again is being used to evaluate the viability of ARM-based CPUs for production workloads at CEA. So, given it's already been mentioned, I thought I'd put this in as well. It's not just these big vendor systems. ARM is being deployed in the cloud. The biggest kind of news version being the AWS deployment of the Graviton cores. But then you've also got companies like Verne Global offering HPC as a service and dedicated instances based on both the ThunderX1, and certainly that's used in the packet system, but also the ThunderX2 systems that are coming online. And I just wanted to put this into perspective quickly by Googling the pricing for the Amazon instances. You are literally talking cents to rent a 16-core ARM system. Now, this isn't top bin performance, but it's the same instruction set as the ThunderX 2. So all of the software ecosystem exists on this system, and it's rentable by the hour. So in terms of getting applications ported to an ARM-based system, in terms of testing out software, gaining some experience on the system, this is frankly the most economical way that you could possibly be doing it. And we have examples and Docker images of everything to deploy HPC-based software stacks onto these Graviton instances. So software is really important for us, and this was one of the side discussions we were just having in the break of once you reach a certain stage, it's not actually the technology that matters. It's the ecosystem and the experience that that can provide for end users. So I throw this up not because many people particularly use OpenHPC to deploy their systems, but just because of the complexity of the software stack that it represents and the work that goes into maintaining all the packages in the software stack, both by ARM and most importantly, Linaro. And Linaro is one of the kind of commercial extensions of ARM that deals with a lot of the collaboration work. And that's really useful for us. They've been driving OpenHPC and getting all of these packages ported, running and maintained on ARM-based systems. So if this is your preferred route, then you can trust that everything is available where it's not architecture specific. On top of that, ARM actually provides a set of our own tools and software. So we have our own ARM compiler, which is an LLVM-based compiler, and with our Fortran, it's a PGI Flang-based system, though we are working very heavily with the new development of F18, which is also going to be called Flang. Great. But this is a commercially supported product from ARM that operates on top of all of the open source alternatives that you have and all of the vendor provided compilers on ARM. But arguably more important to that is the performance libraries side of things. So this is where we're seeing real inroads in terms of getting performance gains on ARM systems. So we have a set of architecture specific performance libraries, and these are microarchitecture tuned to get the most out of every specific chip that we're providing variants for. So obviously we have a ThunderX 2 variant, and we're shipping a Cortex A72 version as well. When other chips come online, we have optimized versions of the libraries, but the point is to provide an MKL replacement to drop in to have the best BLAS, LARPAC, FFT routines that you can have on a system, but also to have a few of the extra extensions, so optimized transcendentals, vectorized routines, everything that you really need as a scientific developer to get the most out of the hardware if you're not writing these algorithms yourself. So what does that get us? Well, I wanted to keep this as impartial as possible. I didn't want it to be a kind of very biased vendor talk. So all of these are stolen slides from some of our partners. So these are some of the early results from Astra at Sandia. And these are their comparison numbers, albeit quite crudely, against a dual socket Haswell. Obviously we're on to Skylake now, so you need to take this into account when looking at these numbers. But the important thing is that for Sandia, they are seeing improvements in all of their key code domains. And this slide and the work that was published for it actually came out of literally a few weeks of work. They'd had some early access to the systems. But when the Astra system was actually deployed into Sandia, they were able to get their core code base on the open side and the mini apps up and running on this system incredibly fast, but also getting some really good performance numbers out of it. And that was important to them. But it's worth actually digging a bit more into that performance data. ARM isn't the silver bullet that's going to magically make everything faster. It's an instruction set, and that doesn't inherently make it better or worse than any other instruction set. It's all about the implementation and the design decisions that were taken into that implementation. So as I said earlier, the ThunderX2 didn't put a focus on vectorization, but it did put a focus on memory bandwidth. So when you actually break down the performance of a specific code and the kernels that go into that code, when you strong scale it and weak scale if you flip between the graphs, you actually see some incredibly large variation in terms of the performance gains or performance losses for different kernels and different maths operations. So this is something that we have kind of come to expect and are really trying to understand, to know where is best for this particular CPU that is currently available. So obviously routines that are very memory bandwidth intensive get a nice performance boost. Again, this is based against Haswell, so you have a theoretical 2x memory bandwidth gain. So it's seeing some incredibly good performance gains for those routines that are memory bandwidth limited. Those other routines that actually use more CPU intensive instructions, use lots of vectorization, don't get that same performance gains. So this really is about understanding the nature of the applications that you're running on the system and the nature of the hardware that you're running it on, and finding the best chips, the best configurations, and possibly even the best algorithms for your code to make the most of the hardware. So our friends at the University of Bristol have done extensive benchmarking work, and I encourage anyone who's interested to actually go to their GitHub page. They make all of their benchmarks available. They've got the input decks for running them. They've got comparison performance results for different architectures. And this did not come out of ARM, so it's as impartial as it can be. And obviously sometimes the results are good, sometimes they're not as good. But it's really about understanding where in the market these particular ThunderX2 chips are used. Now, this is obviously single node runs. We can then take that data and start looking at the scalability of some of the different codes that they're interested in. And actually what we find here is, because of the high core count with the ARM systems, that the scalability trends aren't exactly what we would have expected based on extrapolation of equivalent Intel systems. So it's more than just looking at single node performance. It's actually looking at those configurations, your MPI counts, OpenMP counts, and then seeing how that scales when you move up onto more nodes. So for those of you that can't read, we're seeing charts up to 160 nodes of this ThunderX2 processor. So just quickly mentioning, one of the reasons why we're able to get this application performance kind of out of the codes quite easily really does come back to this performance library. And this is where a lot of our internal work is going at the moment. We have quite a large team based in our Manchester office, and they sit next to our compiler team. But it's really looking at how they can extract the absolute most from the cores of that specific architecture and making that performance transparent to end users. So it really is drop-in replacement libraries that get you top bin performance from your latest chips. This graph giving a comparison between our ARM performance libraries and FFTW was actually generated, I believe, Friday morning from the very latest drop of the performance libraries. And what we're seeing is pretty much across the board when looking at fast Fourier transforms is that we are significantly outperforming the FFTW implementation. And I should point out that FFTW 338 is actually incredibly well optimized for ARM. So this is really how the added benefit of knowing the specific architecture that you're running on, all of the microarchitecture details can really add to the optimization of a package like FFTW. And so across the board, we're getting about 2.5x speed up. Obviously, for incredibly small sizes, there's a high penalty incurred with all of the optimization, so we don't actually see a performance gain there. But for realistic cases where you're large powers of 2, we're doing some incredibly impressive performance numbers. And this is constantly evolving. So what we do is we take all of that internal optimization knowledge, the knowledge of the architecture, our collaboration with our partners, and really try and reach out into the community. And our goal really is to make ARM a viable alternative to x86. I'm not going to stand up here and say, right, we want to replace every x86 server that's ever been deployed in HPC and the cloud and server, because that's not realistic. What we want to do is enable end users, code groups, developers to consider ARM as a platform to really be able to get the most out of their code. And if it's the right choice for them, obviously great if they can deploy systems based on the ARM technology. But if it's not, then we have to be pragmatic and take that information internally, improve the designs, look at the markets that we're targeting to get the best out of the systems. So this is actually where I sit. I'm a field application engineer. We have a team of us across Europe and across the US. And we sit down and we work with code teams to educate, because that's so important when it comes to the ARM instruction set, to help port their codes and to help optimize their codes. And we get some good success out of this. So I stole this off of Twitter because I didn't actually have the original. But this is one of the outcomes that came from our previous hackathon last week that was located actually in the meeting room just across the corridor. We had a 3-day hackathon with Mellanox and a number of the Dirac code groups, and we got them working on the Catalyst system that's located here at Leicester, and the SwiftSim team were able to get one of their more comprehensive Galaxy simulation codes run across the system and actually start coming out with some good visualizations of their simulation, which was a big achievement in the time that went into it. And so this side of things is really important for us at ARM, and so I wanted to just put in a nice little plug for our next event. Is under the Prace banner. We have a 2-day training in Cambridge at the end of the month, and because it's Prace, everything is paid for, so we really encourage anyone who's interested in learning more about ARM, and I'll be going more into the details of the SVE vector extensions during that workshop, to register, to send some of your code engineers to this, and get some hands-on experience working with ARM. Right, so I promised that I would put some stuff in here about machine learning and AI. So if you go on the ARM website, obviously machine learning is a big buzzword, everyone's involved in it, and ARM has a strong participation in that. So you'll find nice diagrams like this showing the ARM activities, the different layers of optimization that we provide, and all of the hardware that sits underneath that. But this is still in the traditional ARM mentality of looking at mobile phones and looking at low power accelerators, and Mali being our GPU offering. This isn't server class this is still looking at mobile and embedded. So whilst the support's there, it's not really what we want to be talking about in this kind of forum. So the work to actually look at ML and AI as a server candidate has only been fairly recent on ARM. And we've got a fair amount of catching up to do on this, but it's something that we are committed to and actively exploring. So we have build guides for all of the key frameworks that are being deployed. We are running these extensively internally, getting some good performance numbers on this. At the moment, our work has primarily focused on the inference side of things, but there are other initiatives looking at training on this as well. So when we look at the traditional kind of x86 environment for this, you've obviously got your big packages. I'm going to have to remember to get this right, the DNNL now, rather than just calling it MKL, as a primary kind of route into running your packages on an x86 system. Now, with the work that's going into that, they're hopefully open sourcing that fairly soon, so that will become an option on new architectures. But what we're providing is an added layer through our performance libraries. Now, this is a stripped down version of it, targeting just the core components that are more relevant to the machine learning and AI frameworks, rather than the kind of strong double precision routines that are in the existing performance libraries. But this is a performance library light to provide the acceleration on ARM-based systems. And there's a lot of work going into the optimization of these gem routines that are giving some really good performance gains, even though this is incredibly early on in its lifespan. So this is fairly new to us, especially within the server side of things, but it's something that we're really committed to and are seeing some good results. I wasn't allowed to actually present any of the scaling numbers that we've got for this because it's too soon, I'm told, but everyone internally is quite happy with the performance that we're getting out of it. So I just wanted to bring this back to the collaboration side of things. This week we actually have one of the STFC funded early career placements that Mark spoke about in his talk. We have this candidate starting with us later in the week, and he will be spending 6 months looking at the wider use of ML within HPC. So looking at its applicability within applications, how the optimization libraries can actually be used to support the algorithms that are being used in that, and how we can really find the synergy between machine learning techniques, AI techniques, and the HPC applications that sit on the more traditional side of ARM's background. So we're going to be using the existing deployed Catalyst system for this, and being able to get some of the applications and frameworks really targeted towards some of the Dirac use cases and the problems that are facing the Dirac codes on ARM systems. Right, just a quick, essentially, conclusion. So what's next? Well, when you're talking ARM, it's always quite difficult because we're not manufacturing anything, but the point is you will continue to see lots more coming with an ARM basis. So there are lots of vendors producing chips. There are future roadmaps from a number of different companies that will be producing viable server class CPU offerings within the next kind of year, 18 months. You'll really start to see an increase in CPU offerings, and they will be targeting different segments. So I haven't even spoken about things like EPI, that are going on and the work that's happening there, but there's a lot that is going on in this, and continually whilst that's happening on the hardware side, we're making sure that the ecosystem and the user experience that they get on that hardware is up to scratch and what people would expect when using any server class hardware. Based on these chips, you'll be seeing more deployments, larger scale, and more importantly, more applications. And again, this is really important for us because the more we can do to get applications up and running on ARM, especially working with ISVs, really breaks down that barrier to entry for people interested in adopting ARM in a production setting, not just as a research project. So we'll see more of that and more of a community built around that. And for that, ARM commits to providing a long-term roadmap. So we've got a Neoverse roadmap that's providing the IP roadmap for the next 5 to 10 years of what we are making available to our partners who want to manufacture chips. We're investing in the software side of things. I've already mentioned F18 briefly. But more importantly, it's support for our customers and people that actually want to use these ARM systems. And that is looking at applications, software, and performance. And the best thing that I can encourage people to do is to get involved in that initiative. We're really trying to build this ecosystem and this community. So we have our developer websites, our ecosystem websites, where there's all the kind of news, events, and everything like that. Obviously for us, supercomputing is the next big event, and we have a number of user groups, BOFs, collaboration talks that are going on during that week. So for those who are interested in learning more, getting hands-on experience, come and talk to us, engage with us, talk to our partners, and we should be able to really get people involved in looking at ARM as a viable option for HPC. Thank you.